data analysis. Okay, so things don't get any better than that. Okay, you know that your data analysis model is wrong, but it's good. It's good enough. It's useful. And so you would think that if you simulate using that same model, then things can't get any better than that, because that means that the underlying model is in fact the correct model, right? I mean, you don't know that when you have real data. You just make an assumption and you say, I have a model with sources of variability in it, and I'm going to assume that it's good enough or useful. But now with simulated data, we can actually say, we'll see how good these methods are if we simulate the real data. Sounds like they kind of lost connection. Oh, it says low battery. So, Todd, this microphone has a low battery. You may want to bring it in or come in and get bring a new battery. I said technical issues this morning.
It's a Monday.
Yeah, exactly. All right. So let's, what I'm going to do is I'm going to try to pick up some data, an Excel spreadsheet, and we'll go from there. But let's just first of all review a few things so that we know exactly what we're going to simulate. Now we can simulate with R, or we can simulate with most any software package. We'll start off using Excel, and let's see here. There's my connection. This little device has got an icon that covers everything up. Okay, those of you in class now can see the same thing, I think, that the students are seeing, and or the online students are seeing. And so what is the model that we have used for our data set for? Okay, so we say that we're interested in some trait, yield, right? And we say that that thing is equal to some overall average. And then what else do we have in the model?
Environment effects.
Okay, then we also have some sort of environmental effects. We'll
genotype effects or line effects.
Some sort of genotype effects. But when we also have these things replicated, we had a randomized complete block. And so in the original model, before we figured out some things were not influencing, we had this block, right? So we had these blocks that were nested inside environments. I don't remember exactly how to write this, but we had these K blocks nested within the J environments. And then somebody said we had genotypes. And then what else do we have?
Genotype by environment.
We have some sort of genotype by environment interaction. Now, some people wrote this, and I've corrected it, but they were saying genotypes were nested within environments. And that can be done. It is possible to do that. But in this data set, we didn't have genotypes nested inside environments. We didn't have genotypes nested inside blocks within genotype. So one of the sort of a classic way of doing this is you can say, have a split plot kind of design where you might spray one side of the field and not the other, and so you might have genotypes nested within environments where one environment is sprayed and the other side is not. But that was not what we have here. We have them completely cross effect, and then there's always some sort of residual. Okay. Do we have any other? Oh, we also said that there was maturity was entering into this. So there's some sort of slope associated with a covariate that we use the letter M for it, and that this covariate in the end, we could have said, well, each slope and each for maturity and each genotype maturity, we could say that we have these maturities for the genotypes, and they're unique for every environment. We have a different slope. We already have said that we have a different intercept for the environments. Okay, but we also have these, and so we'll get around to adding this covariate in our simulations. But let's start off a little bit simpler. Let's just say we don't have this covariate called maturity. So let's just say we're going to start off with a model for our now. We're going to simulate a set of data that and so we're going to start off with this little bit simpler model, and we'll think about covariates after a while. We need to have a data set, Excel spreadsheet. Let me see if I can download. This may be what I'm looking for. We'll find out as we go. Okay. So we're going to have some, that's called simulation sheet. Yeah, so we have some lines. We have some environments.
Do you want us to be able to see this?
Oh, you not see this?
No, you still have the only one.
Oh.
Okay. So we have some lines, and I don't know how many lines there are. Let's take a look. It's like there's 19 lines. Okay, and I've got blocks within environments or reps within environments. So I've got these 19 lines, and if it's a randomized complete block sign, then each of these blocks has all 19 in. And that's all at environment A, right? And then let's just say I have another environment. This is environment B, and then there's a block. Now, you'll notice that I use the notation where I say block. I don't have blocks 1 and 2 again, because blocks are never the same as you go from one environment to the next. These are unique blocks. It's always a good idea to start getting in the habit of not saying, oh, this is rep 1 and 2 in this environment, and then we start over again, rep 1 and 2 in the next environment. No, they're not the same. They're really different. So name them differently so that you don't end up with problems later on. I need to quickly check to make sure. Chelsea, can you hear me at all? Okay, just want to make sure because the microphone isn't working. All right, but those are sources of variability, lines, environments, reps within environments, and then I have something called a M or mean, right? So we have so far in our environments, and we have an overall mean. And we have blocks within environments. We have these genotypes. We have these. But the genotypes are just labels right now. They don't have any particular value. So I've got a mean that, at this point, I'm just going to say in this particular environment, and for that matter, all environments, my overall mean is 60 units. Okay. Doesn't matter where I am, the mean of everything is 60 units. And then I've got some environments. And these environments I think of as being fixed effects, right? So, but they're deviations from the mean. So they're either deviations of -7 units or +7 units, okay? There's two environments. And then I've got some sort of genotypic value. Now these genotypic values here, where do these things come from? How do we want to think about the genotypic values? How do we simulate those? We said they're random effects, right? And so they should be deviations around 0. How should they be distributed? Same thing with the residual. Got some values here. How did I come up with these values? Are they just magic values? How did I do that?
And probably it shows it from a standard, or I guess not a standard normal, but.
Yeah. So let's talk about how to simulate random numbers, first of all. So some of you have done this before. You said, I'd like a random number between 0 and 1. Rand, you got to type in equals. So we just want a random number between 0 and 1. And we want that number to be a uniform random variable. Sometimes you all have used that to help you select. Okay. And so all I want is some random number between 0 and 1. And I can get a lot of random numbers between 0 and 1. I don't know how it looks to me like I've got 10,000 or 1,000 of these things over here. And so there's some random numbers between 0 and 1. Random uniform, 0, 1. Okay, so that's just column heading. This is, I've got some random numbers. Now, we've said though that our residual errors are equal to some sort of normal we make an assumption about the residuals. So let's bring that back over here. In our modeling, we have said that these residuals are IID normal, 0, and some standard deviation. Okay, we make that assumption. Now, they might not be that way, but we make that assumption whenever we do this analysis of variance. So what we're going to do right now is we're going to say, okay, we're going to generate some random numbers that are distributed not as a uniform random variable, but as a random normal variable with a mean at 0. Let's just figure out the code for doing that. And so this is going to be residual distributed normal 0.
You can see.
Okay. Residual normal 0, 1. Okay. So that says the standard deviation of 1. What's the variance?
1.
1.
Square.
Yeah. So this is some random number, and how do I generate that thing? Well, next week or on Wednesday I'll show you the theory of why this works. It's not intuitively obvious if you don't. For right now, whoops, I don't want that. Now, why did it do that?
Because you're still actively in the cell. So if you hit return, then you'll be able to.
All right. So what this is saying is pick a random number between 0 and 1, random uniform number, and use that as a seed, if you will, for the inverse of the normal distribution. And normal distribution needs to have a 0 mean and a standard deviation of 1, not 7. An equal sign out here. And so that's just how to do it. That's just how to write that thing. Okay? And so you get a random number now that says 1.35. Okay? That comes from a normal distribution. That's just sampling the normal distribution. You say, okay, I'm going to get a 1.35. That's with a standard deviation of 1. And you end up with an array of these things, and if you took the sum of these things, you find that they're equal to 0. Now, sometimes we want the random normal distribution to be bigger than 1. Okay. How big? So this is the same way let's talk about the genotypic, genotypic effects. What do we assume about these genotypic effects? Well, we know they have a mean of 0, right? Because that's what we use for our model. But what else do we know about them? These things are also independent and identically distributed, right? And turns out we assume they're normal. Okay, so the genotypes we assume are also normally distributed.
So this might be a stupid question, but why do we assume that the genetic values are IID when most of the time you're going to be dealing with populations that are related to varying extents?
Related to what?
To each other. Like the populations, the lines within the population are related to each other to varying extents.
Yeah, and I'm not sure that it makes I'm not sure what you're asking, because I don't know that it changes any of this.
I don't know, I was just thinking that like if you have lines, if you have, you know, maybe 5 families within what you're screening here, then you wouldn't expect them to necessarily be IID within a family.
Among families, but within families, if they're all additive genetically, and you're just taking a sample of lines from within a family.
Yeah.
Then within a family, they would all have the same.
It'd all be IID within, but not
Yeah, but
once
the
you
variance,
combine.
yeah, that's right. The variance may change as you go from family to family. That's, although we can do that.
Okay.
We can deal with that because each family can have a different variance. And that's certainly the case. When we're dealing with traits that are not, don't have genetic architectures of very large numbers of genes, okay, made up of, you know, many QTL, let's just say we have a gene that, we only have one gene and it's dominant. Well, in that case, what do we have as a distribution for that genotype? Or for that trait?
It's categorical.
Well, certainly it's categorical, although it's very easy to make with large enough error, it's very easy to make it look, the phenotype to look very continuous. Learn how to do that. But in that case, we would simulate it as a binomial random variable. And we'd say any values for this binomial that are greater than 0.75, you're going to get one value for the genotype, and any that are less than 0.75, you're going to get another value. Okay, and then you can add error to it and end up with a distribution that can actually appear to be very normal because the error is distributed as a normal. And so, yeah, it's entirely possible to do that. And those are, you know, things that you should play with. You know, you should say, okay, what if I only have 2 genotypes? Meaning I have either homozygous for big A's and homozygous for little a's. And so I have, and that particular locus is the only locus that controls the trait. But I have a lot of noise, a lot of residual variability. What would my distribution for the phenotype look like? That's what we're learning how to do right now. Okay, but yeah, we do make an assumption that and we can have different variances for each family. For these data that we're dealing with right here, since they're not aggregated by families or any relationships, we don't build that into it. In the same sense that it's possible to have a covariate that is related to the trait you're interested in, it's possible to have individuals be related to each other. Within a family, they're all related the same, but between families, they can be varying levels of relationship. That means they have varying levels of covariance between them, and it's possible to simulate the covariance. But for right now, the easy thing to do is we have 0 and then we have some standard deviation for the genotypes. In our data, how big was the variance for genotypes relative to the residual variance? Data set 4. Do you remember? What was the magnitude of it? Remember? Using
The moments.
I think about 2.5 times.
the genotypic variance was about 2.5 times larger.
And the residual.
The variance or the standard deviation?
I think the variance.
Yeah, I don't remember right
Or
off the top of my head
something.
either, but you can go back and look at applied learning activity number 3 or number 1, and using the mixed linear model. You can quickly take a look at that. If you can find that. I don't keep any of that, any of your assignments on this computer.
Line was actually less than residual. So
Okay.
residual was about 3 times, yeah. 3 times that of line.
Okay, what was the residual variance?
It was 117. 117.
117 was the variance.
Yeah.
So the square root of that is what?
About 11 points.
About 11. Okay, so let's say that what we're going to do here for our residual, we're going to make that 11. Okay, that's the residual variability. Now we'll have some values that are consistent with the real data. It won't be exactly the same, but you'll find out that the estimate from this is not going to be exactly 11. It's going to be off because you're sampling. You're sampling from a distribution that has a variance of 117. What was the variance for the lines?
37. Okay, 38, yeah.
38. So that means change this to 11. And then what we're going to do is we're going to say genotypes are distributed as normal, let's see, normal, 0, and what was the, you said 37 or something?
Yeah, about 6.
So we'll just say 6?
Yeah.
Okay, good. I'm going to copy that thing over there. Here's that one. That one. 6. Okay. So now I have some genotypic values, some residual values, and we can now, I think, put together a phenotype, right? So let's go do that. So I've got this phenotype here. It's going to be equal to a mean and then some fixed effective environments. And then we have some sort of genotypic value and some sort of residual value. So I'm going to replace these numbers here with the numbers I just generated, right? I'll go back there, and I'm going to paste special, because I want the values, I don't want, okay? So now I've got some values there for that, and I also need to do it for this. Okay, so now by phenotype, if we look at it, it's the sum of these things here, just like we did before. Now what have I done wrong here for this simulation? I've done something wrong.
I guess we don't have G by E.
Well, we don't have G by E, but let's just say for right now, yeah, and we also have to ask how big is the G by E piece. But let's just keep it. Let's just keep it within the environment. What have I done wrong within the environment? So I have these genotypic values, and these genotypic values are the same for that genotype, whether it's in block 1 or block 2 or block 3 or environment 7 or whatever. Okay, so that means that this genotypic value, even though it comes from a random normal distribution, but for those first 19, I wasn't supposed to do that. Copy them. Okay, what I need to do with those is I now need to copy those, right? To the second rep, the second block. Now I have some repeatability for the genotypic values.
So that's to apply the genotypic value to the same lines in each.
Yeah, it has to be, that's right. It may be from a random sample, but if you go from one line, if you go from that same line, you go the same line in another replication, that genotypic value should stay the same. It should stay the same when you go to a new environment. And both replications in that new environment. Okay. Now, get rid of all this other stuff. How about the replicates? Do I need to play that same game with the residual variability? No, I don't want to repeat that stuff.
It's unique.
Yeah, that's right. That's stuff that's not in the model. So you go ahead and say, it's a random sample for every one. Okay, so now we've got the phenotypes and the question is, and it's from a couple of environments, and we can ask questions about, we can start doing all the exploratory data analyses that we've done before. Okay, you're ready to go with it. There's a G by E question also that Boris pointed out. So how do we go about simulating G by E? This turns out to be really hard. There's a paper, and I don't know if I put it into your set of reading materials or not. Let me look real quick. Modules. That. I'm supposed to be able to get to the view that you guys have. I don't see that I'm able to do that. Normally I can ask for the student view, and right now I'm not able to get the student view. Not clear to me why not. Well, let's see, there's probably another way to get to this. Ah, that's the, no, that's not. No, I did. I'll get it. It's mathematically difficult to read. It takes a lot of reading, but I'll put it in there. It's a manuscript by Jody Edwards and John Luke Jennings that most people haven't really paid attention to. It was published in 2002 or something like that. And it isn't about simulations. What it is about, however, is G by E, and they describe in there how they go about doing G by E and how they simulated it. And but it was, they were mainly interested in other questions about G by E. But one of the things that you can do, we've been working on these patterns of G by E, right? We said, well, there's certain patterns that we see in our data, and the question is, can we recreate those patterns for G by E? Well, we've already got two different kinds of environments, right? There's some high yielding and some low yielding environments. We've got that. Now, the G by E piece, how would you go about using your G? Would you just simply multiply your G value by your E value? And that's a possibility. Take the two of those and multiply them together. And then divide by some inflation factor. Keep it from blowing up on you. The way that Edwards and Jennings suggested doing this is to say, well, I'm going to, for each environment, I'm going to sample some distribution in the same way I'm sampling the distributions for the G and the residuals. Okay, and so you can also create a distribution for G by E with the magnitude. And you can say, well, as I go from one environment to the next, I'm going to change that distribution. What do we call that when we do that? We call that heterogeneity, right? So we have this heterogeneity that we saw in some environments. We had different, because right now we have no heterogeneity. Our genotypes are the same in this environment relative to each other as they are in the next environment, right? So we could say, all right, I'll keep the ranking of my genotypes the same, but I'll spread them out or shrink them down. That's one way to do it. Another way is to just say, okay, I'm going to put my genotypes into an environment, and in that environment, there's going to be some inflationary factor, and in the next one, it's not. And we can sample that from a distribution, how much you want to inflate it or not inflate it. I'm going to let you all think about that for a while this week. I don't want to, spend too much time on this because you've got this exam. Has anybody looked at the exam at this point?
I glanced at it.
Okay. It probably ought to look pretty much just the way your ALAs look today. The early questions on the exam have not been in an ALA, they were the examples. So the example code and the example ALAs, I think there were 4 or 5 example ALAs, in which I demonstrate how to do exploratory data analyses. That's what you need to go and pick up those examples to figure out your how to do the exploratory data analysis. Are there any aspects of the description of the exam, the background on this that are at all confusing to you? Remember, the first thing to do is figure out what the heck the objective is. And what's the objective of this breeding program? Let's just take a look at the, can you see the exam at this point? I'm not even sure you can.
Mm-hmm.
Yeah.
Okay.
I have it downloaded.
All right. Okay, so we've got these barley cultivars. And so we have more than one trait. There's one that, there's a whole bunch of brewing characteristics that they have to adhere to. And I just said, we're gonna have something called malting quality. It represents all of those. And what happens is that currently what people do is they do a lot of shipping of barley out of the western states to other parts of the country that brew beer. Almost all of Iowa's barley comes from Idaho, for example. And the question is, you know, when there's pressure, meaning market pressure for locally grown products, people in the Southeast have wanted to start growing their barley themselves, but they've got to grow them in the Southeast locally. And that means probably growing them in the winter months. And so that's a different kind of barley than what grows in the summer months in the Western mountains. At the very least, it has to deal with higher humidities. It's got to deal with all kinds of different kinds of soils and all that sort of stuff. So anyway, these craft brewers, they wanted to, instead of growing winter wheat, they wanted to grow this winter barley. And they are just sampling a whole bunch of barleys. There's been a barley breeding program in North Carolina for a while, and there's a few other barley breeding programs, winter barley breeding programs. They've been used mainly for feed, animal feed, chickens in particular, but now they want to start using some that, and they're looking for some that have good malting quality. And they want to find two things. They want to find the production site, good production sites, good fields for producing this stuff, so that they can contract with the farmers that own those fields and get them to produce specifically for their local brewery. And that's essentially what this is all about. They need to have these barley varieties grow really fast in the winter. In other words, they don't have to really grow really fast because they can be grazed for a while, but they've got to get them out of the field in time to get soybeans in the field. So they can't have these things sitting out there in May. So that's why earliness is important. And there's a data set that's got some of this stuff. All of that background pretty clear? And there are these things that are, you know, the lines are labeled as E, R, and L. So, and they mean different things. E are the elites, and then there's some L lines that came from the elites. So it turns out they're actually derived out of the elites. And this R line is a line that's generally used for feed. It produces a lot of grain. You know, for the farmer, what matters is if I'm going to contract for this thing, I need to know what barley would normally produce that I could sell as a feed. And so I'm going to compare things to R1. So if I grow one of these craft brewing barleys, I know that I'm going to take a hit on yield. So what am I going to ask as a premium to contract with these barley growers? And so they've got this, they all want this R line in there so that they can make those kind of comparisons. All right, I think we'll let it go at that.
Are you busy tomorrow?
Yeah.
Any questions?
G class.
All right,
Today.
I think we're done. Not sure.
I'm just thinking it can be Wednesday. Or the train start like on Wednesday.
Everything went away. Hopefully it went away for a while.
Actually.
Okay, there's.